Hello, this is Jack Jackson. In this video, we're going to talk some more about volumes found by revolving a region in the XY plane about a vertical or horizontal axis. So volumes of revolution, volumes of solids of revolution. We've introduced the disk and washer methods earlier, but let's talk a little bit this time about answering the question, do we use washers or do we use shells? Do we have a choice? So in theory, actually, one always has a choice of either using the washer method or the cylindrical shell method when computing a volume of revolution by integrating with respect to y or with respect to x. We get to choose which way we draw our strips, vertically or horizontally, and then that's going to lead, one way of drawing it will lead to washers, one way will lead to shells. So we use the cylindrical shells when the strip is parallel to the axis of revolution, and we use washers when the strip is perpendicular to the axis of revolution. So the following table gives us the basic setup for each of the four cases. So what you're going to do in practice is first you have to choose the column depending on where the axis is that you're revolving. So that'll be given. So if we're revolving around a vertical axis, that is x equals a constant, vertical line, then we have to choose one of these two from this column. And if we're revolving around a horizontal axis of revolution, y equals a constant, horizontal line, then we have to choose one of the two from the second column. If we end up with washers, the basic formula is the volume is pi times the integral of r square, say r1 square minus r2 square, times dh. dh is the height, the infinitesimal change in height. Now dh will either be dx or dy depending on which way we slice it. Cylindrical shells method, we use the formula v equals 2 pi times the integral of rh dr, and dr is the infinitesimal change in the radius, which again is going to be dx or dy depending on which way we slice it. And we've in previous videos we kind of illustrated why we get these formulas and what they're for. In this one I want to focus a little bit more on how we choose. So if x equals c is your axis of revolution, we're looking at this column right here, then the height of the strip is the top y minus the bottom y, but they have to be converted to functions of x if we use vertical strips. So if we use vertical strips of width dx, then we're integrating with respect to x, and everything has to be in terms of x. So then we're using the cylindrical shell method here because we have vertical strips and a vertical axis. Those are parallel, so that yields cylindrical shells. The height h of the strip is the top y minus bottom y, so it's just y2 minus y1, but we can't leave them in y's. We got to turn them into functions of x. So it'll basically be, f of x minus g of x or something like that. And these have to be converted to functions of x. And the radius is the distance from x to c, so it's the absolute value of c minus x. If c is bigger than x, if the line is always to the right of your region, then the absolute value of c minus x is just c minus x. But if the line is to the left of the region, then the absolute value of c minus x is x minus c. So use whichever one of those that you want to use. The absolute value of c minus x or x minus c, the absolute value is the same thing. And the limits are set up to cover all the positions of values for the strip, so we let the x go from the lowest x to the upper, and x2 be the upper x. And so that's your basic setup for the integral that you see right there. However, if we want to integrate with respect to y, then we're drawing a horizontal strip. Okay, we're integrating with respect to y. Everything has to be written in terms of y. So now the strip is horizontal, the axis is horizontal. Those are let's see, horizontal strip and a vertical axis, excuse me, those are perpendicular. Yes, so that's going to give us washer method. The outer radius is x minus c for x on the curve farthest from x, or at least the absolute value of that. And the inner radius is absolute value of x minus c for x on the curve closest to there. And these have to be converted to functions of x. And limits are set up to cover all the possibilities again. You know what I'm going to do? I'm actually going to change this up here um, to be x minus c here as well. It doesn't really matter because the absolute value is going to be the same thing. But you're going to use x minus c or c minus x for that absolute value, depending on which one is going to give you a positive value. Okay, and then we get, and in fact, I'm going to do one more thing. I'm going to actually take this here. It is correct as I've stated it, but I'm going to actually put this part right here in absolute value as well. But make sure that if the y, if this is the farthest x, the farthest y, and this is the lower y, then the absolute value can be dropped out and just put parentheses there. But just to be sure we have that. And down here I'm going to do kind of the same thing. I'm going to put absolute value there to make that sort of cover all the possibilities. But you can drop those absolute values if you're sure that you're using the curve for the outer and inner as indicated. Okay, and I'm going to do the same thing over here. So continuing on, let's look at the right column here, where we're assuming that we have a horizontal axis of revolution, y equals c, for that horizontal line that we're revolving around. Now, you still have the choice of breaking up into vertical strips, integrating with respect to x, or horizontal strips and integrating with respect to y. So the outer radius, big R, is y minus c, absolute value, for y on the curve farthest from y equals c, and the inner radius, little r, is y minus c, absolute value, for y on the curve closest to y equals c. But they have to be converted again into x versions. If we're doing anything along here with vertical strips, everything has to be written in terms of x, and of course your dx is your teeny thickness that you have there. Okay, so anyway, there's the outer radius square, there's the inner radius square. Notice I've you know, if you're going just to the x-axis or to the y-axis, then these c's here are 0, but they could be some other number as well. Okay, and so it's basically power square minus power square for the two different radii. So for the washer method. For the cylindrical shell method, you get that again when the horizontal strip, because you have a horizontal axis, those are parallel. So the height is the right x minus the left x, but again, those have to be done in terms of y now. So it's the right x minus the left x, but in terms of y. Okay, so you have to write your formulas in terms of y to set this up like this. Whereas over here, in this row, you have to write your formulas in terms of x. In this row, you have to write your formulas in terms of y. Now, we got a couple of assumptions here. All of this assumes that the axis of revolution does not go through the region, although it could go along a boundary of the region. In practice, each of the following things can give us problems. Okay, first of all, if your axis, if it goes through the region, then you're getting some duplication, so you have to be a little careful there. Another thing is if one or more of the boundary curves may be difficult or impossible to solve for the desired variable. So for example, here you have to, your boundary curve has to be given x as a function of y right here for both ones. Well, it may not be given to you that way. It may be difficult to solve. Okay, so that could be a problem. Or up here you have to solve everything in terms of x. So your upper and lower boundaries have to be written as functions of x. If they're given as functions of y, that may be difficult to set up. When we draw the representative strip, there may not be a consistent curve for the upper and or lower boundary. If this happens, we can get around the problem by breaking the regions into smaller subregions. However, this results in having to set up and evaluate a separate integral for each of these subregions. If we can manage to set up the integral, then we can just use numerical integration technology, such as the Simpson's rule capabilities built into your graphing calculator or computer program, to get an approximate value for the integral. However, if an exact value of the integral is needed, then the resulting integral could be difficult or even impossible to evaluate, so that could be a problem as well. So in practice, what one does is takes the path of least resistance and uses vertical or horizontal strips based upon which one makes the process easier. Either easier to set up the integral, or if they're both equally easy to set up, which one makes the integral easier to evaluate once you get it set up. Now, if they are of equal difficulty, and then either can be used, your choice, or both can be used and then check them against each other. So let's illustrate that with the following set of exercises here. Okay, there are two different revolutions, one about a vertical line and the other about a horizontal line. It's the same region. We'll work out each integral twice, once with vertical strips and once with horizontal strips, so that we'll use the washers and shells on both volumes. Okay, it'll actually be 4 integrals, but only 2 volumes we're calculating, and two shapes we're looking at. Since we don't encounter the potential problems that we listed above in this example, we will be able to finish the problem in both ways, and this will give us a nice check of our work. So here's, if you want to try some of these yourself, this would be a good idea to stop, try these yourself, and then come back. So here are the 4 problems we're going to do. In all 4 cases, we're taking the plane region bounded by the curves y equals x squared and x equals y squared. And then we're doing the following. In part A, we're going to revolve the region about the line y equals -2. Same thing for part B. But in part A, we're going to find the volume resulting solid revolution using the shell method, cylindrical shells, and we're going to use the washer method in part B. And in part C and D, we're going to revolve the region around a vertical line, the line x equals 3. And part C, we're going to get the volume of resulting solid revolution using the shell method, and they're going to use the washer method in D. So if we do it correctly, the answers for A and B should be the same, and the answers for C and D should be the same. So why don't you go ahead and try that now, come back when you've got an answer and check it against what we got here. Press pause now. Okay, so first of all, whichever way we do it, we might want to look at our region. So we've got, both of these are parabolas. We got a parabola opening up and a parabola opening sideways to the right. So these 2 parabolas, if we graph them, x equals y squared and y equals x squared, then where they cross each other is going to be important. And that turns out to be at 0, 0 and 1, 1, which we can see pretty easily. And the area of the plane that's a finite area that's bounded by these 2 is the area that you see shaded here between the 2 curves. So notice that both x and y are going from 0 to 1 for this situation. The top curve was given as x equals y squared, but we might want to solve that for y. Given the part of the curve that we're looking at, y is the positive square root of x. Okay? For that, that's that thicker blue curve there. Y equals square root of x, or x equals y squared, from x and y both going from 0 to 1. Similarly, the green curve, the dark thick green curve, is y equals x squared, and the part we're interested in is x and y both going from 0 to 1, so that could also be solved x equals the square root of y. So that was pretty easy to solve that, x in terms of y or y in terms of x. Even though we had one given each way, it wasn't too hard to solve that. All right, part A, we're going to revolve the region around the line y equals -2. Now that's this red horizontal line down here. That's our axis of revolution. We're going to compute the volume of the solid by revolving it, and it's going to use the cylindrical shell method. Well, if we're going to use cylindrical shells, we need to use strips that are parallel to the axis of revolution. That means a horizontal strip. The thickness of that strip is going to be dy, which means everything's got to be in terms of y. So we're going to do top x is given by y squared, bottom x is given by square root of y. So we're going to use those formulas that are x is given in terms of y. So everything's going to be in y's eventually. The length of our strip here is going to be the height of our cylinder. It's this distance from C to H, given in black here, which is right x minus left x, but given in terms of y. So the right x is square root of y. The left x is y squared. So that's the square root of y minus y squared is the length of that strip. That's going to be the height of our cylindrical shell. So think about rotating or revolving this strip around this axis. It's going to develop a shell. And the radius is going to be this purple distance from C to E, which is 2 to get up to the axis, plus another whatever y is there. So it's 2 plus y, or y plus 2, is going to be our radius. Okay. So again, that's the absolute value of y minus a negative 2, which is just y plus 2. Okay, so let's see what we got here. So regardless of the position of where C is along this curve, or whatever x or y is going from 0 to 1, then what happens is the right is given by the green curve and the left will be given by the blue curve. That's why it's able to set this up as one single integral, because if you had a, like if sometimes the green curve was the right and different time a different curve was on the right, we would have to break that into two different integrals. But with this being a relatively simple region with always a consistent formula for the right side, always a consistent formula for the left side, we're in good shape. Okay, and so here's our integral. It's 2 pi times the radius times the height times the derivative, the dr for the thickness. The thickness is dy. H we said was square root of y minus y squared, and r we said was y plus 2. And then we have our 2 pi out there. Okay, so again, you want to think of this as 2 pi r is the circumference times the height times the thickness, is the easiest way to remember that formula. All right, so now we have it. We just got to finish working it out now. So I just use FOIL here. First times first, that's y times the square root of y. That's y times y to the 1/2 is y to the 3/2. I put it right here. Let's see, the outer product is y times negative y squared. I put that in the front, negative y cubed. The inner product is 2 square root of y, or 2 times y to the 1/2. I put that on the end. And then the last times last, 2 times negative y squared goes right here. And I put those in decreasing order of the powers, although it doesn't really matter what order you put them in. Now, that's just a sum of power functions, so we just use our regular power rule, right? Add 1 to the power, divide by the new power, so that goes 3, goes up to 4, multiply by 1/4. That power 2 goes up to 3, multiply the negative 2 times 1/3. 3/2, add 1 to that. 3/2 plus 2/2 is 5/2, multiply 2 by 2/5. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2, multiplied by 2/3. 2/3 times 2 is 4/3. And then evaluate from 0 to 1. I've left the 2 pi factored out front, so I need 2 pi times the bracket, parentheses minus parentheses. First set of parentheses is this formula with the 1 replacing every y. Second set of parentheses is this formula with 0 replacing every y. All the last parts are all zeros, so that's kind of convenient. And 1 to any power is 1, so we just get the coefficients here. Negative 1/4 minus 2/3 plus 2/5 plus 4/3. The zeros go away. Now we get a common denominator of 3 times 5 times 4, which is 60. Here we're going to multiply top and bottom by 15 to get there, so that's negative 15 for the numerator. Here we're going to multiply top and bottom by 20, so 20 times negative 2 is negative 40. Here we multiply top and bottom by 12 times 2 is the 24. And here we multiply top and bottom by 20 to get 80 for the top. And then just add the numerators, you get 49. This 2 cancels that 60 down to 30. So the final exact answer is 49 pi over 30, or 5.131268, accurate to that many decimal places. Here's the same, we should get the same answer this way. So it's the same region, revolve around the same axis, but this time we're going to use the washer method. To do that, we need a strip that is perpendicular to the axis of revolution, which means we're using vertical strips with thickness dx. So strips where we have a constant x. Okay, and we revolve that around this axis, we're going to get a washer shape. Okay, so what do we get here? Well, we're going to get two radii, right? One is this orange distance from E to D. Well, what is that? That's 2 plus the y here, lower y. Well, that lower y in terms of x is x squared. So it's x squared plus 2 for that lower radius. Okay? And the outer radius is the radius from E all the way up to C. Okay, and so from 0 to C is the upper y, which is square root of x, and to that we need to add the constant 2. So that's the square root of x plus 2. So those are our two radii. Actually, the bigger one is the one with the y, the x equals the square root of x. That's the bigger one, right? So the square root of x plus 2, or 2 plus the square root of x, either way you write it, we square that, minus the inner radius squared, so radius 1 squared minus radius 2 squared, and then multiply by pi. I can bring the pi out front. There should be 2 pi's there. Let me, forgot to delete one of those. There we go, because we took the pi out front, and then it just stays out there. All right, squaring this, you square the first term, multiply and double for the middle, square the last term. Same thing here. Square the first term, multiply double for the middle term, square the last term. Distribute the minus and combine like terms. 4 minus 4 is 0, so that cancels. 4 square root of x plus x, then minus 4x squared, and then minus x to the fourth. All right, so I'm going to rewrite this one as, as a fraction power, and then do it. Find an antiderivative. X to the 1/2, add 1 to that power, x to the 3/2, multiply by 2/3 times 4. Hang on a minute. 1/2 goes up 1, that's 3/2. Multiply by 2/3 times 4 should be 8/3. Maybe that's the only problem because I think the answer is right at the end. This is x squared divided by 2 is 1/2 x squared. This goes up to the 3rd power, multiplied by a 3rd. That goes up to the 5th power, multiplied by 1/5. And I factored out a 30. Yeah, that's right. So when I factored out a 30, that means I'm multiplying everything in here by 30. Factored out a 1/30th and multiply everything in here by 30 to get what's left. The 30 cancels that down to a 10 times 8 is 80. 30 divided by 2 is 15 times 1 is 15. 30 divided by 3 is 10 times negative 4 is negative 40. And 30 divided by 5 is 6 times negative 1 is negative 6. That's essentially the same thing as getting common denominator. I just got that out the front before I start evaluating. Now I'm going to evaluate by plugging in 1 minus and then plugging in 0. Okay, so parentheses minus parentheses. First one is the same function with 1 in place of all the x's in the antiderivative formula, and then 0's here. And by the way, I'm just using the fundamental theorem of calculus. I should be checking to see the function's continuous, but the way I've got it defined alone should tell you that it's continuous, but then also we can look at the formulas and see that this is continuous on this interval at least. Okay, so anyway, moving along here, the 1 to any power is 1, so we get our coefficients 80 plus 15 minus 40 minus 6, and these are all zeros over here. So when we add those coefficients together, you get 49, those constants together. So you get 49 pi over 30 is the exact value, or about 5.131268. 49 pi over 30, love it when a plan comes together. That's the same thing as what we got the other time. So that is a nice check. Completely different way of doing it, and we got the same answer, so that's good. It should be the same answer because those are in fact the exact same volume. Now I've actually written a GeoGebra activity I did this today, this activity calculates the surface of revolution, calculates the volume of that, and it works for any with vertical strips. Okay, so it's going to work for this one here, this version. Of course, the picture that you see for the 3D is the same regardless which way you slice it up. But it provides a lot of detail. There's my link to it for Geogebra, and here's what it looks like in Geogebra. You can put in your formula for the top and bottom. They have to be written in terms of x. So with any time you use a vertical strip, you have to solve those equation boundaries in terms of x. So you have a top and bottom equation, and then you have a left and right limits a and b, which you can enter with the sliders of the box. You have, if you choose a horizontal axis, which is what I've got here, that's going to graph that at y equals c, whatever c is, and I put in the value of -2. So this tells us our axis of revolution is y equals c, or in this case y equals -2. Our inner radius, or radius 1, is the purple distance from E to L. I'm sorry, that's the purple distance from E to U is the top curve, f of x minus c, absolute value. So that's going to be the square root of x minus a -2, which is square root of x plus 2, absolute value, that's just square root of x plus 2. That's what we have there. And then the bottom one is going to be well, it's an orange distance, but you can't really see the orange here, but it's from E to L. And that's going to be the y value here at g of x, which is x squared, minus the c value. So that's g of x is x squared minus a -2 is then x squared minus 2, or x squared plus 2. Absolute value of that is x squared plus 2. So those are our two radii. Take those two radii, square them, and subtract. So that's square root of x minus a -2, or square root of x plus 2 square, minus, and then square root of x squared minus a -2, or x squared plus 2, square that. Subtract those, then, well, absolute value, but if you make sure you start with the one on the top here, you can drop the absolute values, just put parentheses there. And we integrate from 0 to 1, multiply by pi, and we get our approximate answer here of 5.13, which is exactly what we got up here. And you can see the picture here of what the shape looks like. Here's the app right here. This one is the horizontal axis, and this was -2. I can type in the box. There it is, and you can see that. And then, yeah, everything's worked out there, and you can see it over here. So here's your region. The red axis is x, the green is y, the blue coming up out of here is z, and the region is down there, and you revolve around, and you get a shape that looks kind of like this. And I can rotate that around. I have a representative strip drawn here, and that strip can be moved by moving this green point. And as I move that, you can see the washers being formed by that strip over here on the right. So there you get your little washers for different shapes. The washer may be smaller in thickness but wider around here, or whatever, different shapes there. And you can look at that. You can spin this thing around a little bit and look at it. Okay, so I think you'll find that this is useful when you can get everything in terms of x. Okay, now let's go on here. So we've done the first problem two different ways. We did it with vertical and with horizontal strips. Now the second problem, we're going to do it two ways as well. This one we're going to revolve the region around the line x equals 3. And we can use shells or washers here. We're going to use the shells method. Then we have a vertical strip, and the app that we just looked at will take care of this for us as well. This is a volume of revolution of the same area here, but we're revolving around a different line, so we would expect a different shape than we did for A and B, and a different volume, most likely. Now, again, if we're using a vertical strip, the thickness is dx. Everything has to be in terms of x. So you're going to do bottom curve, you're going to do y equals x squared. Top curve, you're going to do y equals square root of x. So the height of our strip is y top minus y bottom, but in terms of x. So it's square root of x minus x squared is that length right there. That's the distance from C to D. You can see there. That's the height. And the radius is this purple distance, which is the distance from C to I. And it's going to be this x value, and then this is 3. So 3 minus that x value is going to be how far it is. Since the x value is to the right of C, the absolute value of 3 minus x is just 3 minus x. Okay, and what do we get? We get 2 pi r h dr for cylindrical shells. Again, think of that as the circumference times the height times the thickness. dr, in this case, is dx. Okay, r is 3 minus x. H is square root of x minus x squared. And then, of course, we have our 2 pi out front. X's are going to run from 0 to 1. Right there. So I use FOIL here and multiply out. 3 times square root of x is here. That's first times first. The outer product is minus 3x squared. Inner product is minus x square root of x. And the last times last is plus x cubed. And if I rewrite this as powers, square root of x is x to the 1/2. So I put that term last. X cubed is the biggest power, so I put it first. Then I got the minus 3x squared. And this is x to the first times x to the 1/2. That's x to the 1 plus 1/2, which is x to the 3/2. And it's negative. All right, well, now that we wrote it in that form, we can find an antiderivative fairly easily. And we just add 1 to the power, divide by the new power. So this is 1/4 x to the 4th minus, let's see, x cubed, divide that by 3. That's negative 1 for the power. Power here goes up 1. 3/2 plus 1 is 3/2 plus 2/2, which is 5/2. Then multiply by the reciprocal, which puts a 2/5 there. And the power here goes up 1. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. Then multiply by 2/3. 2/3 times 3. The 3's cancel and leaves only a 2. Now just evaluate from 0 to 1 because we found our antiderivative. Parentheses minus parentheses inside the bracket there. So the bracket there has the 2 pi out front. The first set of parentheses is this formula with 1's in place of all the x's there. And the same formula there in the second parentheses with 0's in place. All these at the second part are 0, so we get 4 zeros there. The 1 to any power is 1, so we just get the coefficients there. So we get 1/4 minus 1 minus 2/5 plus 2. I got a common denominator 20. So multiply top and bottom by 5 to get 5 there. Multiply top and bottom by 20 to get negative 20 there. Multiply top and bottom by 4 to get negative 8 for the numerator. And multiply top and bottom by 20 and get 40. Or you could have added the 2 and the negative 1 first together and just got 20 for the numerator for that. That would have been fine. So you got 20 plus 5 more is 25. Minus 8 is 17. It's over 20. The 2 and the 20 cancels down to a 10 in the bottom. So the answer is 17 pi over 10, which approximates to be about 5.34. My GeoGebra activity will do that. Let me just go to the actual activity and show you. This time we're going to use vertical axis. So we have this, and the x is 3 this time, right? Wasn't that what we had? Yeah, x was 3, vertical line. So that's over here. There's the radius demonstrated. There's the height demonstrated. There's the integral that we set up and the approximate value. And the shape looks like this here. Let's see if I kind of turn it. So here's our region here in the XY plane. It revolves around, giving a shape kind of like this. You can kind of see the inside and outside of that. And you can also see the strip being rolled around. And what we actually get is a cylindrical shell. If you look at it kind of from the side here, there's no thickness there, or a thickness of dx. So you get a real thin cylindrical shell. each time we have that for the different values of the input x here. Okay, so you have access to that to help illustrate and to work with this. Now the next one, we should get the same answer, and we'll get the same shape, same volume, but a different method. So if we revolve the region again about the line x equals 3, we're going to compute the resulting solid revolution. So again, we have our line here, but this time we're going to use a washer method by using a horizontal slice, letting it be a horizontal line segment for a slice, or horizontal little rectangle that we're going to revolve around and take the limit as it goes to 0 width. And so we have a width of dy, excuse me, dy, and we need to get everything in terms of y. So our upper x is going to be the square root of y, and our lower x is going to be y squared. So we're going to use those formulas for the green and blue curves. This is the washer method this time. So its outer radius is from I to C. So that's 3 minus y squared. And the inner radius is from this red line to the h. So that is 3 minus the square root of y. And that's going to be consistent if we move C up and down. So again, we use the washer method when the strip is perpendicular to the axis of revolution. Okay, so here's our curve. The outer radius is 3 minus y squared. We want to square that. And then subtract. The inner radius is 3 minus the square root of y. Square that. So we square the two radii, subtract, and then multiply by, well then integrate, and then multiply by pi. Thickness is dy, so that's there. Can't forget the dy. And now we do a little algebra here. So square this, we get 9. Square that, we get y to the fourth. Multiply and double for the middle term of negative 6y squared. Similarly, square the first is 9. Square the last is positive y. Multiply and double is negative 6 square root of y. Distribute the minus, combine like terms. The 9, the minus 9 cancel. We get a minus 6y squared, which is here, or y to the fourth, which I put here. That's gone. Plus 6y to the negative 1, which is one way to write that, and then minus y, which I wrote there. So once again, we got a sum of power functions, so we just use the power rule to find an antiderivative. Add 1 to the power and divide by the new power. That's 1/5 y to the fifth. Again, do the same rule here. Adding 1 to the power gives us 3. Dividing negative 6 by 3 gives negative 2. Power goes up 1 here to 2. Divided by the new power gives us negative 1/2 for our coefficient. And finally, y to the 1/2, we're going to add 1 to the power. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And we're going to multiply 6, the coefficient, by the reciprocal of that power, 3/2. 3/2 times 6, the 3's cancel, leaving a 2 times the other 2 is 4. Remember, this is all times pi. Always keep your equals lined up. But our integral sign has disappeared for this point. Now we have to do this evaluation, which is parentheses minus parentheses inside the bracket, because at the end we need to find this first, then multiply by pi. To get the first bracket, first parentheses, we plugged in 1 in place of all the y's and put that there. And the second one, we plug in 0. Once again, all the zeros here go to 0. All the 1 to any power is 1, so we just get the coefficients 1/5 minus 2 minus 1/2 plus 4. And we get a common denominator 10. Multiply top and bottom by 2 here to get a coefficient, get a 2 in the numerator. Multiply top and bottom by 10 to get negative 20 over 10. Multiply top and bottom by 5 to get negative 5 over 10. Multiply top and bottom by 10 to get 40 over 10. So 40 plus 2 is 42. Negative 20 plus negative 25. Negative 5 is negative 25. 42 minus 25 is 17. So it's 17 pi over 10 is our answer. And decimal approximation there is about 5.34. Did we do that already? Yeah, we did that one already. Here's 17 squared, or 17 pi over 10. And here we got, hey, 17 pi over 10. It checks out. All right, so I'm hoping that that helps quite a bit with understanding a little bit about how you set up these types of problems, whether you have washers or shells. It's really time for you to go and do some homework problems now, um, and see what you can come up with. Okay? So happy integrating, happy finding volumes of revolution.